Hello, my name is Ronaldo. I'm a doctoral student at the University of São Paulo, Brazil. Thank you very much, Professor Amano and Session Chairman, for the opportunity to present this paper in this event. I hope that the test drive will be successful and future ECOS conference can also be held online. This is the first time for me. Today, I'm talking about some work that my advisor Silvio and I, together with Drs. Daniel, Julio, and Ciro, developed as part of my doctoral research project. The work is related to the optimization of a combined cycle plant of an offshore power supply hub. This hub is connected by submarine cables to oil and gas production platforms in order to supply electricity more efficiently and with less environmental impact. Offshore production systems with multiple platforms are found in giant oil fields in the Brazilian Pre-Salt, such as Lula, Mero, and Búzios. The motivation for the development of this work lies in the fact that energy forecasts indicate that the global energy demand is expected to grow in the coming decades. Fossil fuels will continue to play a relevant role in the global energy matrix, even in scenarios of rapid transition to a low-carbon economy. Currently, about a third of the worldwide oil production occurs at sea. Brazil is among the top 5, producing offshore about 90% of the country's production. New offshore production systems are expected to come on stream in the coming decades. The financial sector is incorporate climate risk in credit granting, and this is leading operators to take energy efficiency measures to decarbonize new projects. In addition, operators are introducing the internal carbon price to avoid exposing long-term projects to the risk of future carbon taxation in regions that do not currently have this regulation. Electricity and hot water generation system of oil and gas production platforms is by far the main source of greenhouse gases in offshore production. The supply of onshore clean energy is not always financially viable due to the cost of long subsea transmission systems. The same is true for wind farms that need to be set in shallow water, sometimes distant from the oil field. The primary processing plants of the platforms are getting bigger and more energy intensive. The allocation of more efficient systems, which is already a challenge, becomes even more challenging in the case of combined cycle, as it occupies 20 to 50% more area when compared to a simple cycle gas turbine. Therefore, a power hub becomes competitive in face of industry challenges. Moreover, depending on future carbon taxation, the hub could receive carbon capture schemes which is not possible in a conventional platform. This work intends to provide designers with a framework to both compare the performance and optimize the design of the steam bottoming cycle to minimize weight, as it reflects directly on vessel cost, as well as the power plant capital cost and carbon dioxide emissions. In this work, the performance of the utilities plant of a conventional offshore production system containing 4 self-sufficient platforms, that is, platforms capable of producing power and heat internally to supply the vessel demand, is compared with the performance of a production system involving the same 4 platforms, but with power being partially supplied by a central power plant. Fuel gas is supplied to the power hub by the pipeline that exports associated gas to the continent. It's assumed that the 4 platforms have the same electrical and thermal demand, whose behavior throughout its productive life can be seen in the figure in the lower right corner of the screen. Peak power occurs in year 5 with 81 MW, but the lifespan average power is only 46 MW. Similarly, the maximum thermal demand occurs in year 9 with 46 MW, and the lifespan average heat demand is 22 MW. There is a lag of 1 year before each platform starts operating. The useful life of each platform is 25 years, and the power hub remains active throughout the lifespan of the complete production system. In this figure, you can see the control volume of the utilities plant of the offshore production system with the 4 self-sufficient platforms in the production of energy and hot water. This configuration is quite simple. Each platform has 4 Siemens aeroderivative gas turbines model SGT-A35 in 4 at 33% configuration. which means that the utility system has been dimensioned so that at peak, power can be supplied by 3 gas turbines while the fourth remains in backup to increase operational efficiency in the oil and gas production. Each gas turbine is equipped with its own waste heat recovery unit for the production of hot water at 160 degrees Celsius without burning extra fuel. The control volume under analysis in this conventional configuration considers the utility plants of the 4 platforms simultaneously. Fuel gas is the associated gas which can be supplied by the platform's primary processing plant or alternatively by the exporting pipeline, for example, in case of gas processing plant shutdown. On the other hand, the proposed configuration with a power hub adds some complexity to the control volume. Each production platform has only one Siemens SGT-A35 gas turbine with waste heat recovery unit and also 4 hot water boilers with 11.5 MW each, which is capable of supplying the entire vessel's thermal demand even if the gas turbine is out of operation. It's important to note that the hot water boiler has very high energy efficiency throughout the entire operating range, in this case 95%, which is in line with catalog of commercial products. The power hub has 5 combined cycle power blocks equipped with GE LM6000 PF plus aeroderivative gas turbines with single pressure level steam bottoming cycle, 1 steam cycle per gas turbine. The power blocks are arranged in 5 to 25% configuration, which means that at any power there will be at least one power block in backup to increase the power hub availability. The control volume under analysis of the proposed configuration considers the utility plants of the power hub and also 4 platforms simultaneously. Fuel gas of the production platforms is supplied as in the conventional case, and the power hub receives fuel gas from the exporting pipeline. Unlike simple cycle gas turbines, the steam bottoming cycles have some design variables that need to be correctly selected by the designer according to the characteristics of the topping cycle and objectives pursued by the power plant. There are 3 objective functions that need to be considered in order to maximize the technical and financial performance of combined cycles for offshore application. The power plant occupied area is important to minimize the size and thus the capital cost of the hull. The capital cost of the power plant itself is also essential to increase the financial attractiveness of the power hub, and last but not least, the net emission of carbon dioxide per unit of electricity delivered, even more important in scenarios with carbon taxation. The selected design variables and constraints of this work are the steam pressure and temperature in the inlet flange of the steam turbine package. Design simulations were performed by using GTPro software in the ThermoFlow package. As the software does not have an internal optimization tool, but it does communicate with Excel, a Visual Basic script has been developed to bridge GTPro and MATLAB for the optimization. An SGA2 algorithm has been used to optimize the 3 objectives. The criterion for choosing the Pareto solution that best meets the objectives of the combined cycle considers the normalization of the obtained results. The next step is to calculate the distance of each normalized Pareto solution to 0. The solution with the shortest distance was chosen for the design of the steam bottoming cycle. The table shown in this screen also provides the Pareto solutions that minimize or maximize the objectives. Despite the variation of the normalized data, it can be seen that the amplitude variation of objectives 1 in square meter per megawatt, objective 2 in US dollar per kilowatt, and objective 3 in kilogram of CO2 per megawatt hour are all relatively small. Once the design parameters are chosen, The next step is to simulate the results of the combined cycle power block in the GT Master software in order to obtain its off-design performance. The simple cycle gas turbine is also simulated in GT Pro and GT Master. In this case, the waste heat recovery unit has been designed according to the data of a real press-out project. The exergy efficiency of the conventional configuration, here called case 1 in blue, is well below the exergy efficiency of the proposed configuration, here called case 2 in green, throughout the entire lifespan. The addition of the power hub increased the exergy efficiency not only by the fact that the combined cycle power plant is inherently more efficient than a power plant based on simple cycle gas turbine, but also because the power hub is capable of producing the exergy efficiency variation in different field stages. In the battery life, the gap decreases down to 2.6 percentage points in year 12, thus marking a fast performance decline in the conventional configuration. Therefore, the second half of the productive life is remarkably the most challenging scenario for the efficiency of the conventional production system. The operating range of gas turbines in simple cycle and combined cycle has been limited to between 25 and 92% of the rated power to improve the operating stability of the utility system. Analyzing the operational points of the gas turbines of the conventional and proposed configurations in different oil field moments is important to understand the lifespan exergy efficiency. In the battery life, when the exergy efficiency gap reduced to the minimum, the combined cycle gas turbines of the power hub were operating far outside the design point. In addition, at the end life and tail production, the gas turbines of the conventional utility system sometimes operate as low as 50% nominal, which explain in great part the very low exergy efficiency of these oil fields stages. Moreover, the gas turbines in the production platform of the proposed configuration is partially out and the hot water boilers assume the thermal demand. The proposed configuration with the power hub reduced the carbon dioxide emission in all phases of the field's productive life. In absolute terms, the greatest reduction was observed at the production peak. This stage is characterized by high electrical and thermal demand. In the battery life of the oil field, the emissions avoided were lower, which can be justified by the exergy efficiency gain of the conventional configuration. At the end life and tail production stages, emission reduction of the power hub configuration increased again, reaching values close to those observed at the production peak, although with much lower oil and gas production. Here we can see energy and carbon intensities of hydrocarbon production. These indicators reveal a concerning scenario since the environmental impact of conventional self-sufficient platforms deteriorate over time. Battery life basically doubles the kilowatt-hour of power and kilogram of carbon dioxide emitted to exploit 1 barrel of oil equivalent. In addition, in the stage so-called end life, the energy demanded and carbon dioxide emitted to produce 1 barrel of oil equivalent can be 90 times higher than that observed at the production peak. Similarly, during the tail production stage, the energy and carbon intensities can be 19 times higher, which in practice means that the productive life of the oil field can be ended earlier in a scenario with carbon taxation. The performance of the configuration with Power Hub represents an attractive solution to reduce significantly both energy and carbon intensities up to 28% at tail production, being a viable solution to reduce the environmental impact of the offshore oil and gas exploitation. Oil companies normally prefer battery technologies in offshore production development projects due to the huge amount of capital and operating risks involved. Deep water and ultra-deep water oil fields with multiple platforms may benefit from combined cycle power hubs. Performance indicators show the great advantage of the Power Hub compared to the conventional platform designs. Multi-objective optimization approach adds flexibility to the designer to select the most appropriate set of variables in order to obtain the optimum Pareto-front solution. The benefits of the Power Hub should be investigated in more details to replace the conventional utility system, especially at the second half of the field lifespan. Utility system of design performance and production platform loads indirectly related with the hydrocarbon production. For example, living quarters, ballast, etc. penalize both energy and carbon intensities. Thank you. If you have any question, just let me know.